Welcome back to the PMHNP Podcast, the definitive podcast for those passionate about mental health throughout every stage of life. Whether you're an aspiring professional or a seasoned expert or someone simply keen on understanding the intricate world of psychiatric care, you're in the right place. I'm Dr. John Rossi, a certified PMHMP, nurse educator, and lead content creator and instructor at Clarity Education Systems and www.pmhmptesting.com. We've got a pretty big episode today. This is a topic that you either love or you hate. There's really no in between, but it is one that is vitally important to your career as a PMHMP and providing that real quality of care for your patient, while at the same time making sure that your clinic and everyone that you work with is up to date on the current and most applicable evidence-based practices out there. So we're going to be talking about evidence-based care, looking at statistics and study designs and levels of significance. All of it, it's a lot, and I know it can get overwhelming, but this is a very key area on your certification exam. If you've already taken it, you know what I'm talking about. If you're preparing for it, you're probably stressed about it. So hopefully after today and using this podcast with the seminars that you're preparing with over at Clarity and www.PMHNP testing within the student portal, you'll feel more confident in understanding how all of these really work and are integrated into not only your practice, but your growth in practice and how we are helping establish the future of healthcare through evidence-based. So evidence-based care, this really refers to healthcare practices that are built on the best available scientific knowledge. It means making decisions about the care of an individual patient or their families based on the available evidence, right? So combining with clinical expertise and the values and preferences of those individual patients and their families. So the aim is to provide the most effective and efficient care to patients to improve health outcomes. That is really the ultimate goal of evidence-based care. So we do have some key components of evidence-based care. First, it's the best available evidence. This involves using high-quality, current, and relevant research findings, including systematic reviews, randomized controlled trials, observational studies, and other research designs to form and inform the clinical practice. We'll talk about those in depth at the end of the podcast because I want to leave you with probably, in my opinion, the most important thing to understand are those levels of evidence, because you're definitely going to see questions about that on the exam. Clinical expertise, this is another component. So this refers to the knowledge, skills, and experience of healthcare providers. Clinical expertise helps in the application of research evidence, and individual patients are able to apply that evidence in their care practices as you create these care plans and interventions based on your expertise that is based on the most current available evidence out there, taking into consideration their specific conditions and their specific circumstances, speaking of the patient. And then finally, we have patient values and preferences. So this component, it really acknowledges the importance of considering the values, preferences, needs, concerns of that patient, and then making clinical decisions based on those values and preferences, based on your clinical expertise, based on the available evidence. So this is really a crucial part of patient-centered care as it respects the autonomy, right, of the patient, and it also encourages that shared decision-making process between you as the provider and the patient. Remember, on the exam, everything is always patient-centered, even when we're talking about statistics and evidence-based care. So the process of evidence-based care is done by implementing evidence-based key points and key steps. And these we're gonna go over 5 of them. And this is how we're going to go through that overall process of establishing best practices in evidence-based care. So first we have to ask, right? We formulate a clear and concise clinical question related to a patient's problem. Then we search for the best available evidence to answer the clinical question. You cannot acquire if you haven't asked the question first. Next, we're going to appraise. This is critically assessing the quality, relevance, and applicability of the found evidence. then apply, integrate the evidence with the clinical expertise and patient values and their preferences to make an informed clinical decision. And then finally, we're going to assess. This involves evaluating the outcomes of the decision and then adjust the care plan as we need to or as necessary. So what is the importance of evidence-based care? Well, first, it improves patient outcomes, right? It leads to a more effective and efficient care, potentially resulting in better health outcomes for the patient and could also mean their family as well. It reduces variability in care by promoting consistency in care based on decisions that are standardized with proven interventions. It enhances patient safety. This helps to identify and apply safe and effective interventions, thereby minimizing the risks to the patient. This also helps us to optimize healthcare resources, evidence-based care. By identifying the most effective interventions, it helps in utilizing resources efficiently, right? Avoiding wasteful or harmful practices. Then we have facilitating shared decision making. This enables healthcare providers and patients to make more informed decisions collaboratively, respecting individual preferences and also those individual values that the patient may have. So there are some notable challenges in implementing evidence-based care. First is keeping up with the volume of research that's out there, especially with, the internet and social media and everything else that helps flow the information. There's this rapid proliferation of medical research, and it can make it challenging for healthcare providers to stay current. Access to research. Obviously, there's limited access to full-text articles and subscription-based journals. This can impede the acquisition of evidence that's available to healthcare providers. Maybe they just don't have the amount of money because their practice is struggling, or they just don't have the revenue in order to subscribe to all of these research subscription-based journals. So we can have this limited access to care or research care. Then we also see a lot of time constraints, right? The time required to search and appraise the literature. This can be a barrier for clinicians. Patient complexity, right? Individual patient variability. And then the complexity in making these difficult to apply evidences in this uniform way. So that way it applies to most patients in most situations under the appropriate diagnoses. So there's just this inherent complexity with evidence-based care at times. And then ultimately we see a resistance to change. There may be that resistance from healthcare providers to go away from established practices and routines. So there's that inherent barrier that can exist when wanting to change, just based on evidence-based care that may be out there. So despite these challenges, evidence-based care remains that cornerstone of modern healthcare. We have to overcome those challenges, striving to optimize clinical outcomes and then enhancing quality of care. So ensuring quality care while managing costs effectively can be quite challenging, okay? However, several methods exist and strategies that can be employed to strike a balance between quality and cost, aiming to achieve appropriate outcomes that we're looking for our patients. So utilizing evidence-based care can lead to improved patient outcomes by reducing unnecessary interventions and managing costs effectively. We enhance smooth communication and collaboration among different healthcare providers through proper care coordination, therefore reducing duplication of services and improve patient outcomes. We're going to utilize health information technology, employing electronic healthcare records or EHRs and other health IT solutions in order to, enhance those decision-making and reduce errors and improve efficiency. Then we also have that patient-centered medical home or PCMH and team-based care plan models. This implements and encourages team-based care to improve satisfaction, healthcare outcomes, and potentially reducing costs. So all of this is tied to evidence-based practice, and we use it to enhance the way that we practice, the way that we save money for healthcare systems, and ultimately save money for the patient while providing consistent and supported evidence-based care. Okay, so let's go ahead and move on to what we're going to call the meat and potatoes of this evidence-based discussion. So data analysis. Now this is integral to converting raw data into meaningful information in order to drive decisions in healthcare, especially in areas such as quality safety, fiscal management, and then things like daily operations. So several data analysis techniques are applicable to this to this discussion. First, we're going to look at descriptive statistics. So how do we apply descriptive statistics? Now, this is used to summarize and describe the main features of a data set. We do this by using mean, median, mode, range, and standard deviations. It helps in understanding the basic features of the data in quality, safety monitoring, and daily operational metrics. Then we have comparative analysis. This involves comparing data to identify patterns and differences. We use things like t-tests, ANOVA, or chi-squared tests. This is very useful in comparing performance, financial outcomes, and patient safety incidents across different units or different time periods. Trend analysis, this examines data points collected over time to identify trends, right? So time series analysis, moving averages, this is ideal for monitoring key performance indicators, financial metrics, and then patient safety trends over a specific period of time. Regression analysis, this investigates the relationship between a dependent variable and one or more independent variables. So we use things like linear regression or logistic regression. It helps in predicting outcomes and understanding the relationships between the variables, such as costs and patient outcomes. Then we have predictive analytics. This utilizes statistical algorithms and machine learning techniques to identify the likelihood of future outcomes. We use things like decision trees, neural networks, and forecasting models. So predictive analytics enables the anticipation of future events, optimizing resource allocation, and then identifying patients at risk. Okay, stick with me. I know there's a lot of terminology, but you need to know each one of these in order to not only apply them in your practice, but especially for the certification exam. Okay, so next is a root cause analysis. Want to foot stomp this one? Often shows up on certification exam questions. So root cause analysis. The application for this is a systematic process for identifying the origin of problems or events and then establishing the causal factors. We use things like fishbone diagrams or 5 whys analysis. This aids in identifying the underlying causes of quality and safety incidents, facilitating the development of effective interventions, and that's really the key of root cause analysis. We also have cost-benefit analysis. This compares the cost of an action or intervention to its expected benefits. So net presentation value, or NPV, is a technique. We also have internal rate of return, or the IRR. Utility for this is essential for making fiscal decisions and prioritizing interventions based on their economic value. That is a part of your PMHNP practice. Then we have something called benchmarking. And so benchmarking compares an organization's processes and performance metrics to industry bests or best practices from other industries. So we're going to use performance metrics comparisons or gap analysis in order to utilize benchmarking. The utility of this is that it's useful in establishing performance standards in quality, safety, and operations, and also identifying areas of improvement. Then we also have data visualizations. So we use these data visuals in elements like charts, graphs, or maps to represent information and patterns within the data itself. These are things like dashboards, heat maps, scatterplots, linear maps, enhancing the understanding of data sets by providing this visual interpretation of the data and then aiding in identifying those patterns, those trends, and those insights in a quick manner. Then we have process mining. So process mining utilizes event logs to analyze and visualize healthcare processes. Sequence clustering or transition matrices are certain techniques that are used in process mining. So this offers insights into efficiency and conformance, supporting process optimization in daily operations as well. Okay, quality control charts. We've all heard of them, and there's a good reason why. So quality control charts monitor the quality of processes over time. We use things like run charts or control charts. This helps in monitoring variations in processes and identifying any of those out-of-control processes in quality and safety that we really need to focus in on and potentially use other research techniques to come up with better ways of handling quality control. Then there's something called sensitivity analysis, and this really determines how different values of an independent variable impact a particular dependent variable under a given set of assumptions. So we use techniques like what-if analysis or scenario analysis for this. It's useful in assessing the robustness of healthcare operations and financial models against various uncertainties. All right, then there's one that you may not have heard about. This is the Monte Carlo simulation. So this uses randomness in order to solve problems that might be deterministic in principle, especially useful in risk analysis. Okay, so techniques include random sampling and probability distributions. So what is the utility of Monte Carlo? So this provides a range of possible outcomes and then the probabilities that they will occur for any choice of action, aiding in decision-making in fiscal and operational areas. So pretty interesting one for sure. So we really need to understand, we've got, all of these trends and data analyses, utilizations, but what is data versus what is information? There is a clear difference between data and information. So data refers to raw, unprocessed facts and details without context. This is usually collected as a result of observations, measurements, or experiments. Data can be quantitative or qualitative and exist in various forms such as numbers, text, images, sound, or other things. It doesn't have to have meaning in itself, right? And often needs to be structured and analyzed in order for it to be useful. So an example of data would be a collection of numbers, right? 98.6, 99.1, 100.4, 101.3, all of this representing the body temperatures of different individuals. Then we have information. So information is data that has been processed, organized, structured, and then presented in a given context so that it has meaningful and valuable information to the person who receives it. So it is data that has been interpreted, right, and understood within context and is relevant to the question or the decision at hand. So an example of information would be a statement that says the average body temperature of the group is 99.85 degrees Fahrenheit, with one individual having a fever at 101.3 degrees Fahrenheit. So that statement represents information derived from the raw data that we previously talked about in the example of data. So what is the relationship between data and information? Well, it's a strong one. So the relationship between these two is sequential. Data is the raw material that is processed and analyzed to extract meaningful insights, i.e. information, right? And then the transformation from data to information involves various processes, and this includes organizing. So arranging data in a structured manner, categorizing it, and then indexing it. Analyzing that data, examining the data to discover patterns, relationships, anomalies, trends, etc. Interpreting that data, understanding and explaining the patterns and trends discovered during the analysis. And then we want to contextualize it, relating that interpreted data to a specific situation or problem to make it meaningful and applicable. So erroneous or incomplete data can be dangerous, especially in healthcare, particularly in critical domains within healthcare optimization, intervention planning, finances of healthcare, and this is for several reasons, right? So impaired data decision-making can impact these decisions based on inaccurate or incomplete data that leads to inaccurate conclusions and inappropriate actions. So in healthcare, inaccurate data can lead to incorrect diagnoses and treatment plans. This potentially could cause harm to the patient. We also see reduction in trust and credibility. So erroneous data undermines the reliability and credibility of data resources and sources and their systems. This leads to a loss of trust among the users and the stakeholders. An example of this would be a financial institution may suffer a loss of customer trust and reputation due to errors in account balances or transaction records. Same thing can be applied to a provider that uses data inappropriately to intervene on behalf of a patient with bipolar 1 disorder in a manic episode, prescribing the wrong medication based on the symptoms that present. Are we really talking about bipolar 1 or are we talking about bipolar 2? There are key differences in the manic presentations, and our therapy will change based on the presenting information. So data is super important. We also see compromised safety. So incomplete or incorrect data jeopardizes safety in various areas. Examples, let's use an example in aviation. So incorrect data inputs can affect navigation and communication systems. That is really applicable to healthcare if you think about it. And this potentially leads to accidents, just like in healthcare. Then we have an issue of wasted resources as well. So resources may be allocated inefficiently or ineffectively based on inaccurate data, leading to waste and inefficiency, right? So an example of this would be erroneous demand forecasting in manufacturing. That leads to overproduction, underproduction, and then resource misallocation, which is disastrous for any organization or business. There are also some key legal and compliance risk issues here. So compliance with laws and regulations may be compromised due to that inaccurate reporting or record keeping, leading to legal repercussions. So an example of this would be like incorrect financial reporting that can result in legal penalties and then damage to a company's reputation. We're seeing that today with some instances that took place in Florida with inappropriate billing for Medicaid, Medicare by a nurse practitioner, and we're talking millions upon millions of dollars. So this has not only hurt that clinical practice, but it's also set back the progression of nurse practitioners within that state because of poor data and then poor compliance within the laws and regulations itself. So very, very important stuff to consider with the legal and compliance issues. Okay, research and validity. So scientific research and studies based on inaccurate or incomplete data can yield invalid results and conclusions. So clinical research based on erroneous patient data may lead to incorrect findings, and then this could overall affect drug development when you think about it, which impacts everything that we do as nurse practitioners. Strategic misalignment. So incorrect data can lead to misguided strategies and objectives that do not align with the actual needs and realities of the organization. So how do we mitigate all these risks? We talked about quite a bit of them. So in order to mitigate the risks associated with erroneous or incomplete data, we should employ data quality management practices. And this includes data validation and verification. We ensure that data is accurate and conforms to specified formats and values. We're very, very specific with this. Data cleaning, identifying and correcting errors and inconsistencies in data in order to improve its accuracy. Data profiling, assessing the quality of data and its suitability in order to serve its intended purposes. And then data governance, establishing policies, practices, and certain standards in order to manage and ensure the quality of that data. So addressing data quality proactively can help organizations avoid the danger associated with erroneous or incomplete data and enable them to make informed and reliable decisions. So that's you as a provider as well as the organizations that you work for. Okay, next let's talk about variables. So variables are often confused with one another, so we really need to recognize how variables in research are categorized into 4 levels of measurement, each of which has unique characteristics and can be analyzed using specific statistical methods. Okay, so first one we're going to look at is the nominal level. So the characteristics of nominal level are is that it categorizes data without a meaningful order or ranking. This is distinct categories and they're identified by names, labels, and classifications. So some examples of nominal level data or variables include gender, be it male, female, non-binary, whatever we want to categorize it as. Another example would be blood type. So nominal level, gender, blood type, A, B, AB, O, whatever it may be. Now, how do we analyze nominal level information? With mode, chi-squared tests, and cross tabulations. Next is ordinal level. So the characteristics of ordinal level include data with a meaningful order or rank. It's really in the name, right? Order, ordinal. So the distance between rankings is not uniform and cannot be quantified. So an example of ordinal level would be pain level, low, medium, high, or customer satisfactions, unsatisfied, neutral, satisfied. And we analyze this by a median, rank order correlation, and non-parametric statistical testing. Third is interval level. So these characteristics are numeric scale with a meaningful order and equal intervals between the values. There's no absolute 0 point. So 0 does not imply the absence of quantity, though. So examples of interval include temperature in Celsius or Fahrenheit, and then IQ scores. And we analyze interval level by mean and standard deviation. This is like t-tests and the ANOVA, regression analysis. Fourth, we have ratio level. So ratio, this is another numeric scale with a meaningful order, equal intervals, and an absolute 0 point. So the ratio of two measurements is meaningful. Examples of this would be height and weight, or income and age. You can see how this has an absolute 0 point tied to those. We analyze this with geometric mean, harmonic mean. We do ratio comparisons, and then parametric statistical testing. So why is this useful? How do we use these specific variables, talking about nominal, ordinal, interval, and ratio within healthcare? Well, in healthcare research, we understand the level of measurement of variables because it is crucial to dictate the type of statistical analysis that can then be performed. So that nominal and ordinal levels are typically used for categorizing and ranking non-numeric or discrete numeric data, such as that patient satisfaction or symptom severity, right? And then again, to review, the interval and ratio levels are used for analyzing continuous numeric data, such as patient vitals and lab results, allowing for a broader range of statistical analysis. So choosing the appropriate statistical method based on the level of measurement, this ensures that we have validity and reliability of the research findings, and then it also facilitates meaningful interpretation of that data. The level of measurement of a variable is crucial in research and data analysis for obviously several reasons, impacting the choice of statistical method and the accuracy of the analysis and the validity of the conclusions that we draw. So, selection of statistical tests. Why does this matter? Why is it so important for us to understand this? Well, different levels of measurement require different statistical tests and measures of central tendency. So, using an incorrect test for a given level of measurement can lead to invalid results, right? And we want to avoid that at all costs. So an example of this would be non-parametric tests are suitable for ordinal data, while parametric tests are appropriate for interval and ratio data. This leads us to that analysis accuracy. So higher levels of measurement, interval and ratio, provide more detailed and precise information, allowing for more accurate and sophisticated analyses. So ratio data allows for the calculation of mean, which is more precise measurement of central tendency than the median or mode used for ordinal and nominal data, respectively. Okay, so I know it gets a little convoluted here, a little muddy in the water, but understanding the selection of statistical tests is super important when looking at those variables. So then we have inferential statistics. This is the level of measurement impacts the ability to make inferences about populations based on those samples in order to determine relationships or differences between the variables. So example of inferential statistics include correlation and regression analyses. This requires at least interval level data to determine a relationship between variables, and ordinal data might be that really might not suffice for making valid inferences, right? All right, next is the validity of conclusions. So why does this matter? So drawing meaningful and valid conclusions from the data depends on how you understand the limitations imposed by the level of measurement. So an example, conclusions about the average or mean are not valid for ordinal and nominal data, where median and mode are more appropriate. Okay, measurement precision. The level of measurement affects the precision with which the variable is measured, right? So it's impacting the granularity and the richness of that particular data set. So an example of measurement precision would be interval and ratio level measurements that are capturing that subtle variations in the variable, providing more detailed information compared to the ordinal and nominal levels. Then we have scale sensitivity. So higher measurement levels can detect smaller differences between the variables and are more sensitive to variations in the actual data itself. So an interval scale can detect the precise degree of difference between two values, whereas that ordinal scale can only rank them in a particular order. Research design and hypothesis testing. Very, very important concepts to understand. So knowing the level of measurement is crucial for formulating those research questions, the hypothesis, and then designing research studies in order to ensure that the research, all of the objectives that we're trying to go after are met. So an example of this would be the formulation of a hypothesis about the differences between groups or relationships between variables depending on the appropriate level of measurement. Then we have data transformation. So the level of measurement impacts how data can be transferred, transformed, aggregated, or converted, affecting the subsequent analysis and those interpretations. So data can be converted from a higher level of measurement to a lower one. An example would be a ratio to ordinal, but not typically vice versa without there being some type of loss of information. So by respecting the level of measurement in designing studies, selecting analytical methods, and then interpreting these results, we can ensure that the rigor, reliability, and the validity of these findings ultimately contribute to the advancement of knowledge within our respective fields, and in our case, in the psychiatric care field. All right, next let's talk about frequencies. So frequencies in data sets can be represented in various ways, and each of them are serving a unique purpose in describing the distribution of data. Okay, so distribution of data as it pertains to frequency. And let's go over a quick overview of each of these. First up we have is absolute frequency. This is the count of occurrences of each value or category in a data set. We identify the most common and rare value or category within that data set. And an example of absolute frequency would be a survey of pet preference, where 50 people preferred a dog and 30 people preferred a cat. Those counts. Then we have relative frequency, and this is our percentages. So the proportion of occurrences of a value or category relative to the total number of observations, usually, like I said, expressed in a percentage. So this is when we compare frequencies in different categories when the total counts may differ. An example, like we just talked about with the preferences of an animal, dog is 62.5% versus cat at 37.5%. Then we have cumulative relative frequency. The accumulated relative frequency of a value or category considering all the previous values or categories. So identifying the distribution of data and the percentile of a specific value or category. So in a survey with ordered categories, category A, 20%, category B, which is A plus B, 50%. Then we have group frequency distribution with class intervals. The organization of numerical data into classes or intervals displaying the count or the frequency of observations in each class. And the use of this is summarizing large data sets and identifying patterns or trends in the distribution of the data. For example, in an age survey, 10 to 20 years, 15, 21 to 30 years, 25. So how many people do we have in the 10 to 20 category? 15. 21 to 30-year-old category, 25. Then we have graphic distributions, and so this is that graphical representation of frequency distributions using charts or graphs. It visualizes the distribution, the shape, the spread of the data set, and then facilitates understanding and interpretation. Examples of these graphics include histograms, bar charts, and pie charts. Obviously, these are graphic representations of that data set. So frequency distributions describe how the values of a variable are spread or distributed, and they can exhibit various shapes and characteristics, right? That's what we just talked about with those graphical representations. So now let's look at a breakdown of some of the common shapes and characteristics of frequency distributions. So first we have unimodal, bimodal, and multimodal. So unimodal is a distribution with one peak or mode. Bimodal is that distribution with two distinct peaks or modes. And then multimodal is a distribution with more than two peaks or modes. And we can really use this in terms of describing the number of prominent peaks within a distribution, which can give insight into the underlying groups or clusters within the data. Then we have symmetric and asymmetric. So symmetric is that distribution where the left and right sides are mirror images of each other. Asymmetric, or what we term as skewed, this is a distribution where one tail is longer or fatter than the other tail. We use this to describe the overall shape of the distribution, and this gives insight into the balance of the data sheet. Then we have negative or positive skew. So negative skew, which is also referred to as a left skew, this is the left tail longer or fatter, and the majority of values are concentrated on the right side. And the positive skew or the right skew, the right tail is longer or fatter, and the majority of values are concentrated on the left side. So the skewness of a distribution provides insights into the extent and the direction of the asymmetry. All right, let's go ahead and move on to normal distribution. So normal distribution is a symmetric unimodal distribution that is characterized with a bell curve, with mean, median, and mode being equal. Properties include approximately 68% of the data falling within one standard deviation of the mean, 95% within two standard deviations of the mean, and then 99.7% within three standard deviations. So you can see how that will kind of bell out as you go from the center point. And the normal distribution is foundational in statistics, and it's used in various statistical tests and procedures due to its well-understood properties. So, understanding the shape and characteristic for this data analysis. It influences the choice of the statistical methods and tests. It provides insights into the central tendency, the variability, and the overall pattern of data. And then it helps in identifying anomalies, outliers, and patterns within the data set. This all assists in making informed decisions and predictions based on the properties. So this gives us that visual representation that we're looking for in those histograms, box plots, and density plots. This will give us that distribution aid, and then it helps researchers understand the nature of the data as it applies to appropriate analysis and strategical pathways. So the concept of frequency in statistics refers to the number of times a specific value occurs in a data set, right? So the simplest way to calculate the frequency of a value is to count the number of times it appears. So for absolute value, frequency is going to equal the count of a specific value in the data set. So if you have a list of values, you can tally each unique value's occurrence to find its frequency. So an example would just be having a list of numbers where you have a data set of 2, 3, 2, 4, 3, 5, and 2, okay? So to find the frequency, we count the number of 2s, which in this case would be 3 times, the number of 3s, 2 times, the number of 4s that appear 1 time, and the number of 5 that appears, and that's also 1 time. So that's going to give you the frequency of each number. Then we have relative frequency. This is used to calculate the relative frequency of a value, and you find it by dividing the absolute frequency of that value by the total number of observations in the data set. So relative frequency equals the frequency of a specific value divided by the total number of observations. Then we have cumulative frequency. So cumulative frequency is calculated by adding the frequencies of each value to the sum of the frequencies of all the previous values. So an example for relative and cumulative frequencies. So continuing from that previous example that I just gave, the data set, we're going to say it has 77 values. For 2, that's listed in those numbers that I gave you earlier, the relative frequency would be 3 out of 7, which is 0.43. And the cumulative frequency would be 3, as it's the first value. For 3, our relative frequency would be 2, because we had 2 3s in that list, divided by 7, because we had a total of 7 numbers. That's going to give you an RF of 0.29, and a cumulative frequency of 3 plus 2 equaling 5, and then so on and so forth. So these calculations enable a detailed understanding of the distribution of values within the data set. Again, this offers a really good look into patterns, relationships, and trends. Okay, so the measure of central tendency in a single value describes the way in which a set of data cluster around a central value or point. It's a way to describe the center of the data set, right? So there are 3 main measures of central tendency: the mean, the median, and the mode. So we're going to talk about each one of those because they're super important to know, and you need to know how to calculate them. So I'm going to try my best to describe it here in this podcast, but I am also going to upload a file that will give you examples on how to calculate each one of these. So hopefully I can get that to work out. If it doesn't, and you are wanting a copy of this so you've got it in a nice central location, just shoot me an email at info@pmhmptesting.com, and I can get you that Word document so that you have it in front of you at all times. So let's first talk about mean. So mean, and this is, we're talking about an arithmetic mean or the average, right? So the formula for mean is going to be what we refer to as the X bar, okay? So we have this little X with a bar over the top of it, and it's going to equal the summation notation, which almost looks like an M that's been turned up on its side. And then we have X divided by N, where X is going to be all of the X values, and then N is going to be the number of items within that sample. So the mean is used when the data distribution is symmetric and there are no outliers. So the biggest characteristic for the mean is that it is sensitive to extreme values, or what we know as outliers. Then we have the median. So the median is just the middle value of the data set when the data points are arranged in ascending or descending order. So if the data set has an odd number of observations, the median is in the middle number. If the data set is an even number of observations, the median is the average of the two middle numbers. And we just talked about how to calculate that average. So the median is used when the data distribution is skewed and there are outliers. Characteristics: the median is not affected by extreme values. So there's a key difference in when you would want to use the mean as opposed to the median. Then we have mode. So the mode is the value that appears most frequently in the data set. We identify the value that occurs with the highest frequency, right? We just talked about how we identify the frequency. So the mode is used for categorical data and when the most common item is of interest. So a data set can have one mode, unimodal, more than one mode, multimodal, no mode, if no number repeats. All right, so why is the measure of central tendency so important? It provides a summary statistic that represents the center point or typical value of the data set. It offers a way to reduce data complexity, simplifying the data interpretation. It enables comparisons between data sets or between values within the data set. So which measure do we need to use? Okay, we've kind of talked about that, but let's look at it a little closer here. So the mean is suitable for interval and ratio data, specifically when the data are symmetrically distributed. Then we have the median, which is suitable for ordinal, interval, and ratio data, especially when the data are more skewed or have outliers. And then we have mode, which is suitable for nominal data and for finding the most common category or value in the data set. So let's try to do an example here. It's going to be hard, obviously, because we're talking. But for a data set, when we have 1, 2, 2, 3, and 4. So the mean is going to be adding 1 plus 2 plus 2 plus 3 plus 4, which is going to give us 12. And then we're going to divide that by the total number that is represented, which there are 5 numbers. So 12 divided by 5, which is 2.4, that's going to get us that mean. Now for the median, 2. So it appears as it appears in the middle value when the data are ordered. So 1, 2, 2, 3, 4, our median is going to be 2. And then our mode, as it appears most frequently, is 2 because it's there the most. So each of these measures of central tendency provides that different perspective on central location of the data. And then the appropriate measure used depends on those characteristics that you're looking for and what you're trying to find and whether or not there's outliers. So when the count of elements in a data set is even, there is no single middle value. So the median is calculated as the average of the two middle values, right? We talked about that a little bit ago. And in the uploaded document, I'm going to teach you how to calculate that. It's super simple to find, and it should be an easy way to find these numbers. Hopefully you'll be able to use these simple formulations and use them in your homework if you're still in school, or if you're not and you're one of those providers that loves to do research, you can hopefully utilize it in your daily practices. Okay, so let's go ahead and move on to deviation. So deviation scores are values that represent the difference between each individual score in a data set and the mean of that data set. So they are used to calculate the variability or dispersion of the data set and are crucial in statistical analyses, such as the calculation of variance and the calculation of standard deviation. So please go to www.pmhmptesting.com or join our Facebook group, and you'll be able to see these calculation examples in the document that I'm going to upload in conjunction with this podcast. All right, so we talk about those deviations. So how do we interpret this information? A deviation score of 0 indicates that the value is exactly the mean of the data set. A positive deviation score indicates that the value is above the mean, and a negative deviation score indicates that the value is obviously below the mean. So how do we apply it in variance and standard deviation? So deviation scores, they're essential in calculating that variance and standard deviation in order to measure the spread of data points in a data set. Again, find those calculations in the corresponding document that I've prepared to go along with this podcast. So deviation scores, variance, and standard deviation are crucial. Oh my gosh, they're so critical for understanding the dispersion and variability of the data set. This allows for, again, that informed, precise statistical analysis. So all very important calculations and things that you need to know at a very minimum level in order to pass not only the certification exam, but to continue on with understanding statistics within your practice and finding evidence-based works that have been calculated and utilized appropriately based on the data that they have in order to give you, really good information regarding interventions and clinical outcomes for patients and what you should be doing as a clinician based on the most current evidence-based research. All right. Hopefully you're still with me. You haven't given up on us yet with all of this statistical talk, but it is really important, right? So before we move on to the last section today, I want to go over odds ratio and confidence intervals because you will see these a lot in your data and in the papers that you're reading and in your articles, and quite honestly, our definition game on for the certification review. So the odds ratio and the confidence interval, these are commonly used metrics in epidemiology, biostatistics, and then various healthcare fields where the relationship between the variable is studied, or the variables are studied. So we're gonna break these down. So odds ratio, often written as an OR. So the odds ratio is a measure of association between the exposure and an outcome. So again, let's say that again. So the odds ratio is a measure of association between an exposure and an outcome. It tells us the odds of an outcome occurring given the exposure compared to the odds of the outcome occurring without the exposure. So how do we interpret this? So an OR, or an odds ratio of 1, this is going to imply that the event is equally likely in both groups. An odds ratio greater than 1 implies that the event is more likely in the exposed group. And an OR less than 1 implies that the event is less likely in the exposed group. So an example of this would be in a study examining the association between smoking and lung cancer. If the OR is 2.5, it means that smokers have a 2.5 times the odds of developing lung cancer compared to non-smokers. So then let's look at confidence interval, also known as CI. So the confidence intervals give a range in which we are fairly confident the true population parameter, or the true odds ratio, lies. So it provides information about the precision and uncertainty of our estimate. Common confidence intervals are 95% and 99%, but others are also utilized. We just typically see 95 and 99. So how do we interpret confidence intervals? So if the 95% CI for an OR, and you always have to have OR, or odds ratio, in order to list a confidence interval. So if 95% CI for an OR includes 1, okay, so we're going to have two number points here, like, 0.01, comma, 1.2. So that would include 1. Then the results are not statistically significant at the 0.05 level because OR of 1 indicates no association. If that 95% confidence interval for an OR does not include 1, then the results are statistically significant at a 0.05 or a p.05 level. So an example of this, when using, we're going to use that previous example that I just gave with smoking and lung cancer. If the OR is 2.5, which is what we stated before, with a confidence interval, a 95% confidence interval, listed as 1.5, comma, 4.0, so we've got the upper and lower levels, it suggests that we are 95% confident that the true odds ratio lies between 1.5 and 4. Since this interval does not include 1, the association between smoking and lung cancer is statistically significant. So it is essential to recognize that statistical significance does not necessarily equate to clinical or practical significance. Just because a finding is statistically significant doesn't mean it's a great magnitude or importance in the real world. Both the OR and the CI should be considered in the context of the broader scientific and clinical picture. So remember that while the odds ratio, or OR, can provide information about the direction and the strength of an association, it does not establish causation. Additional research, ideally from randomized controlled trials, is often needed to draw that firmer conclusion about causality. All right, so that was a good overview of OR and CI. I'm going to include this information in written form as well in that uploaded document with the calculations for mean, median, and mode, and I think deviations as well. All right, so we have arrived at the end of this podcast, and we're going to go over research quality real quick. Definitely game on the certification exam. They will ask you research quality questions. So research quality can be assessed across various levels and different types of studies. And this comes with their strengths and their weaknesses. So here is a general hierarchical structure. So we're going to look at it from the top down that we often use in healthcare research. But it's applicable to any discipline as we categorize research quality from highest to lowest. So highest level, number 1, are going to be your systematic reviews and your meta-analyses. So systematic reviews, this is the comprehensive review that analyze and synthesize the available evidence on a particular topic, adhering to strict methodology. Okay, so synthesize the evidence of a particular topic is the systematic review. Different from the meta-analysis, still the top tier, but a meta-analysis is a statistical technique that combines data from multiple studies to derive a pooled estimate of effect, often offering a more robust finding, right? So we have a question. Let's say we have a kiddo with ADHD and we want to know what the best treatment option is for this child. We can go in and look for research that has done a meta-analysis. So it's going to be very specific to ADHD treatment options. And then we'll be able to take all of these pooled documents and articles to come up with an analysis that we can feel confident in when choosing what is the best evidence out there for a particular medication management, for example, for ADHD. Little different than systematic reviews, but systematic reviews, meta-analysis, top tier, highest level of research quality. Right below that, we have randomized controlled trials, also known as RCTs. So the definition of an RCT, this is an experiment that assigns participants randomly to different groups. So this would be like a treatment and a control group. And this is all done to evaluate the effectiveness of the intervention. What is the strength of an RCT? It's that random allocation. This helps to control for confounding variables, offering a strong level of evidence. Below that, we have number 3, which is cohort studies. So the definition of a cohort is an observational study. This allows for a group of individuals or a cohort to be observed over time to look at the relationship between exposure and subsequent outcomes. So different than an experiment, we're talking about an observation here. The strength of a cohort study is it's suitable for studying multiple outcomes, and it can provide good evidence in situations where an RCT, it's just not feasible. So below that, we have number 4, which is a case control study. So a case control study is an observational study that's going to begin with the identification of individuals with a particular outcome or case, and then those without it. This is going to be our control. Then we look backward to identify exposure differences. And the strengths of a case control study, it's particularly useful for studying rare outcomes or rare diseases. All right, next up, we have cross-sectional studies. So cross-sectional studies are observational studies that assess both exposures and outcomes at a single point in time. So there is a key limitation when dealing with cross-sectional studies. Again, this is number 5 on our list. So as we go higher in number on the list, that's less, we're going to trust it less. Or maybe not, trust isn't a good word for it, but it's not going to have as high of quality. So that cross-sectional study, this can identify associations, but it is limited in its establishing temporal relationships. So definitely some limitations with the cross-sectional study. Number 6 is a case report or a case series. So this is descriptive studies that focus on an individual case report or a small group of individuals or a case series with a particular condition or an outcome. Some key limitations here. So generally low evidence level because it really lacks the comparison groups and it may not be generalizable to the entire population that you're looking at or other populations. Number 7 on the list is expert opinion or editorials. So these are articles that present the viewpoint of a professional and the insights of experts within the field. So while they may be experts and they've been at it a while, it's really based on their expert judgment rather than empirical evidence. So it's considered a lower level of evidence. So other considerations that you may want to look at, again, these are very low, but let's go ahead and list them, are going to be quality and bias. So the internal validity of a study at each level can vary. Thus, we have a study that will be evaluated for risk of bias, such as selection bias, information bias, and confounding. So all of these need to be considered when looking at research quality. Relevance. Even high-quality research should be assessed for its relevance and applicability to the specific context or population that it's being applied to. Just because it's, really high on our list as far as quality, maybe it's not relevant to our population or the population that it's looking at. And then there are some key ethical considerations. So high-quality research must adhere to strict ethical guidelines and ensure that the participant has his or her or their rights being well established and prioritized. So very important considerations when talking about research quality. All right. So what are the major statistical reporting methods? So statistical reporting is fundamental to that evidence-based research. Different studies might employ varied statistical methods depending on their design, their objectives, and the nature of the data that's being collected. So we have descriptive statistics. This measures that central tendency that we talked about, the mean, median, and mode, and range, variance, standard deviation, and all of these are measures of dispersion within descriptive statistics. And then we look at the frequency distribution too, the count, the percentage, and the frequency of various categories or values. So that's descriptive. Then we have inferential statistics. So this is when we use t-tests. This is used to compare the means between two groups. An ANOVA, or an analysis of variance, this is used to compare the means among 3 or more groups. And then a chi-squared test, this is used to determine if there is significant association between two categorical variables. So these are all inferential. Can we infer? And we use the t-test, the ANOVA, and the chi-squared test. We also have regression analysis. This is when we use linear regression. So this examines a linear relationship between a dependent variable and one or more independent variables. We have logistic regression as well within the regression analysis. This is used to model the probability of a binary outcome based on one or more predictor variables. Then we have survival analysis. So this is the Kaplan-Meier estimator, estimates survival functions from lifetime data. We have the Cox proportional hazards model, explores the relationship between the survival of a participant and one or more predictor variables within that survival analysis. We have non-parametric testing, the Mann-Whitney U-test. You've probably heard of that one. This compares differences between two individual groups when the dependent variable is not normally distributed. We have the Wilcoxon signed rank test, very, very common in healthcare research. This is also a non-parametric test that comprises two related samples or repeated measurements on a single sample. Okay, last I want to talk about meta-analyses. So meta-analyses techniques, this is fixed effect and random effects models. These provide an overall effect size from several studies that examined the same research hypothesis. Okay, so correlation analysis also has to be considered too. So Pearson's correlation coefficient measures the linear relationship between two continuous variables. factor analysis, and principal component analysis. This is often referred to as PCA. So this is used to explore the large data sets and identify underlying relationships between the variables. Reporting of p-values, confidence intervals, and effect sizes. So we talked about CIs a little bit earlier, but p-values and effect sizes. So a p-value indicates whether the observed data fall within a certain range of a specified statistical model. The confidence interval, again, that provides that range in which we can be certain a parameter lies to a particular degree of confidence. And then the effect size, this is a situation that quantifies the size of the difference between groups and the strength of the relationship between the variables. And one thing that I realized we didn't talk about is what are variables? Let's go ahead and define the dependent and independent variables real quick. So in research studies and statistical analysis, understanding that distinction between dependent and independent variables is going to help you to understand exactly what you're looking at and what's actually being evaluated and researched. So let's talk about specific definitions for dependent variable. So this definition, a dependent variable is what you measure in the experiment and what is affected during the experiment. So it's dependent because it relies on changes in the independent variable. So an example of a dependent variable would include if you're examining the impact of different study techniques on test scores. So the test scores would be the dependent variable because they may change depending on the study technique used. So what are some of the characteristics of the DV, or the dependent variable? So it's measured variable, it's quantitatively measured, recorded, and observed. The outcome variable would be often considered the outcome or the result of the study, and then the response variable is the response to the change in the independent variable. So let's talk about then the independent variable, or IV. So the definition of an IV, the independent variable, is what you, the scientist or the researcher, change or manipulate in the experiment. It is presumed that changes in the independent variable cause changes in the dependent variable. So an example of this would be, using the same scenario that we used with studying, the study techniques would be the independent variable because you, as the researcher or scientist, can change or manipulate them. So what are some of the characteristics of the IV? Manipulated variable. It's intentionally varied or categorized by the researcher. Predictor variable, often seen in influencing and predicting variations in the dependent variable. And then the exposure variable, in observational studies, it's what the groups are exposed to or not exposed to. So let's use an example in context here. So consider a study examining the amount of time spent studying affects students' test scores, right? So the independent variable, again, time spent studying, measured in hours, you believe changes this variable because changes occur in the test scores. And then the dependent variable is the actual test score, measured in marks. You hypothesize this variable to be dependent on the amount of time spent studying. So the dependent variable is what you're trying to explain or predict. It is contingent on the independent variable. And the independent variable is what you manipulate or classify to explore its effect on the dependent variable. Okay, so that should give you a good understanding of both independent and dependent variables, how it applies to statistics, how you need to look at these numbers and different measures in order to analyze the material and create, information based on the data that you've collected. And we've talked about all of that, right? What is data as compared to information itself? So a lot of key information points here. Please take a look at the Word document that was created to help explain some of the calculations. There's a lot more to research out there, but I think an hour of research and quality is probably enough for you today. But this should hopefully really spark your interest in the topic. If not interest, then understanding what you need to really focus in on your studies. This is again not everything. Please make sure that you're in the seminars as you're preparing for your certification exam, because we'll talk about some other key components of research, but definitely understand the level of quality, understand that systematic and meta-analysis are going to be at the top tier, and then all the way down at the bottom, you're going to find things like expert opinions. And taking all of this into account will hopefully not only help you with your certification exam, but as you move forward in your career. Again, I'm Dr. John Rossi with Clarity Education Systems and www.pmhmptesting.com. This podcast has been created to help you understand more about statistics, about quality research, and how it is applied to evidence-based practices. Make sure you check out the Word document associated with this podcast, and I look forward to seeing you in one of our next episodes, or you hearing me in one of the next episodes, however you want to look at it. Whatever it is, I hope you're having a great day, night, morning, afternoon, wherever you are, and we'll see you soon. Bye-bye.